Welcome to The Explainer. So think about this for a second. Every single day, you are interacting with metals that keep our modern world running. From the copper wiring inside your walls to the smartphone sitting right there in your hand, these materials are absolutely essential. But actually getting them out of the ground, well, that is a high-stakes, incredibly intense reality. Today, we're diving into a system that perfectly balances this extreme environment, a mind-blowing process we're calling underground engineering Jenga. And by the end of this explainer, you are going to know exactly why that name fits so perfectly. Because it really all comes down to one massive fundamental question. How do you actually hollow out the earth without the whole thing collapsing right on top of you? I mean, deep earth mining is an intensely hostile environment. You're miles underground, constantly fighting against the crushing weight of gravity, the constant threat of cave-ins, and some pretty toxic dust and exhaust fumes. You definitely can't just dig a massive hole and cross your fingers. Safely extracting thousands of tons of rock from that deep within the earth requires a meticulous, almost perfectly calculated master plan. Okay, let's get right into what that master plan actually looks like. It's a method called AVOCA, which, is a bit of a mouthful. It stands for Air Ventilated Open Cut and Fill with AVOCA Retreating Stopes. But what does that actually mean for the people down there? Essentially, it is a highly mechanized, long-hole open stoping method that uses delayed backfill. It is quite literally the ultimate engineering solution, specifically designed for massive mining regions in places like Australia and Canada, to extract bulk ore safely, efficiently, and with some incredible speed. Now, you can't just use AVOCA anywhere. It's definitely not a one-size-fits-all deal. You actually need some pretty specific geological conditions to pull this off safely. For starters, you need a steeply dipping ore body. We're talking an angle greater than 60 degrees. You also want a moderate to wide ore width, and it's generally meant for moderate to deep underground mines. But honestly, the absolute most critical factor here is rock strength. You need what miners call a competent hanging wall and footwall. In plain English, the rock surrounding the ore has to be exceptionally strong so it can hold its own shape while the extraction is happening. So if the geology checks out, the initial setup begins, and it results in this absolutely massive subterranean structure. I want you to picture an underground skyscraper, but instead of building up into the clouds, we are digging straight down into the crust. You start with a main decline, which acts like your main ramp or elevator shaft. And branching off of that, miners carve out a vertical network of sublevels spaced about 15 to 30 meters apart. Think of those as the different floors of your skyscraper. From there, crosscuts are driven directly into the ore body to act as your hallways and main access points. Once that underground skyscraper is roughed out, the actual mining kicks into gear, and it operates on this rhythmic, highly mechanized 6-step heartbeat. It just flows continuously, starting with development, then moving straight into long-hole drilling, followed by charging and blasting, ore extraction, backfilling, and finally, retreat mining. Because the whole thing is so heavily mechanized, this sequence happens at a remarkably fast pace compared to older, manual mining techniques. Let's actually walk through what happens once that initial development phase is done.
Moving right into step 2, long-hole drilling. This is where you'd literally feel the mine vibrating around you. Initiated from the drill drives, this step brings in massive jumbo drill rigs, usually heavy hitters from companies like Sandvik or Epiroc. Seriously, these things look like giant, terrifying robotic insects from a sci-fi movie. They roar to life and bore these huge diameter holes deep into the rock using either fan or parallel drilling patterns. It's deafeningly loud, unbelievably efficient, and it preps the rock for the main event.
Which brings us right to step 3, charging and blasting. This is just raw sheer force. Those long holes we just bored out, they get precisely packed with explosives. And when they finally blow, they don't just crack the rock. They literally shatter the entire rock face into manageable pieces in massive vertical slices. Depending on how the specific mine is designed, this explosive slicing either works bottom up or top down. Okay, so once the dust finally settles, gravity steps in and does the heavy lifting, dropping all that newly blasted rock down to the lower drop points. That is when the load, haul, dump machines, the LHDs, take over. Picture these massive, mechanized loaders just racing through the pitch-black tunnels, scooping up tons of broken ore. This heavily mechanized operation drastically speeds up what the miners call mucking. But the biggest takeaway here, by using these remote or enclosed machines, it drastically cuts down the need to have humans doing incredibly dangerous manual labor right at the rock face. But here is where we get back to that Jenga metaphor from earlier. You've just blasted and scooped out thousands of tons of rock, which leaves this massive empty void, a stope. Well, if you just keep pulling blocks out of the bottom of a Jenga tower, eventually the whole thing comes crashing down, right? The solution is step 5, the delayed backfill. Before pulling the next section of ore, miners actively pump that empty void full of material. We're talking cemented rock fill, paste fill, or hydraulic fill. This backfill provides immediate ground support, keeps the remaining ore from getting diluted, and ensures the entire regional operation doesn't just collapse on itself. And that sets up the pure genius of step 6, retreat mining. The sequence is designed so miners are always moving progressively backward, away from the access drives. By retreating along the ore body and literally leaning on those previously filled stopes for structural support, worker safety is basically locked in. The miners are continually moving away from the danger zone and are never forced to stand directly underneath unsupported empty earth. But hey, structural cave-ins aren't the only thing trying to kill you down there. Let's talk about the A in AVOCA, air ventilation. This is the invisible lifesaver of the entire operation. Think about it. Massive underground explosions create deadly long-haul blasting fumes. Add in all those heavy diesel machines, and you've got thick dust clouds and toxic exhaust gases everywhere. Managing this underground atmosphere is quite literally a matter of life and death. So, how does this beast actually breathe? It takes a massive infrastructure setup just to keep the air clean that many miles deep into the earth. Fresh air is actively blasted down through dedicated intake raises. We're talking hundreds of cubic meters of air per second. The main access declines essentially double as giant wind tunnels. And to keep it all flowing, these incredibly high-powered ventilation fans drive the circulation, aggressively pushing all that toxic exhaust and dust out of the mine through specific return airways. It is a continuous, completely mechanical respiratory system. To really appreciate why AVOCA is such a game changer, you kind of have to compare it to older methods like cut and fill. Cut and fill mining is super selective and precise, sure, but man, it operates at a significantly slower pace. AVOCA, on the other hand, is a massive technological leap forward. Because it utilizes bulk long-hole stoping and heavy mechanization, you get these high-speed, massive yields. It's basically the difference between carving out a sculpture with a tiny chisel versus clearing a highway with a fleet of bulldozers. Of course, in engineering, there's always a catch, right? It's all about trade-offs. The pros of AVOCA are undeniable. Sky-high productivity, great ore recovery, lower overall operating costs, and vastly improved worker safety thanks to all that remote machinery. But the cons are very real, too. Pumping millions of tons of cemented backfill is crazy expensive. The whole method literally falls apart if your surrounding rock isn't perfectly competent. If you mess up your extraction sequencing, you risk destabilizing the entire mine. And naturally, the power required for those massive ventilation demands is off the charts. But even with those massive challenges, AVOCA remains a go-to method across the globe. Why? Because it literally powers our modern lives. It's an absolute powerhouse for hitting those huge production targets in gold mines, copper mines, zinc-lead mines, and polymetallic deposits. The gold inside your computer chips, the copper running through your home wiring, the zinc in your batteries, all of these vital materials are safely and economically brought to the surface entirely because of this exact engineering sequence. It's honestly like this highly choreographed, mechanized ballet of drilling, blasting, mucking, and filling, all happening thousands of feet underground while we just go about our daily lives up top. The AVOCA method is a massive testament to human ingenuity in one of the absolute most hostile environments on the planet. Which kind of leaves you with a fun, provocative thought to ponder today. If this is the extreme level of engineering it takes just to get the copper for a power cord, what other incredible, invisible marvels are secretly holding up the modern world right beneath our feet? Thanks so much for hanging out with me for this explainer. I really hope it sparked your curiosity to look a little deeper.